So here is the code. Uh, so this is how it starts. First, we read an image. I have two images I'm working with. I have a test image, which is a simple square, and then I have a logo, which is more of a circular blob. We create the window so we can see what the image looks like regularly, and then we go to the chain image function. That starts right here. What this does is this finds the outline of the image in black and white and then sends that to where we get the chain code. So we make a vector, which is a list of black pixels and then a list of white pixels. So what I do here is I iterate through the rows, I iterate through the columns, and then I find the intensity at whatever point x and y is at. If the intensity equals 0, that means we find a black pixel. And then we have a boolean that's called is this pixel an edge, and we first set that to false because we don't know. Then we check all adjacent pixels. If we find one white pixel, then we can assume that it is the pixel is an edge. So once we find that edge as equals true, we get the pixel, we get the coordinates of the pixel we're working with, and we push back those coordinates into our vector. And that coordinates is a simple data struct I created that just contains two floats. And then it'll skip the rest of the calls, checking the adjacent pixels because edges is already equal to true, so it won't check the middle row and it won't check the lower row adjacency for pixels. So in a picture I can describe how it's checking it. So if we find pixel, if we find that pixel, the first thing this program is going to do, check, oops. Alright, that's first check top 3 rows. So we'll look here, 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 oops, here, and it'll check here, check here, check here, and then it's just looking for black pixels. Here, here, and here last. And if any of those are white, then this pixel is considered an edge and it stays. So it's like that. Now if none of the pixels, if all the pixels are black, then we can say that this pixel is inside image. Therefore, it is not an edge. And then on my last check is if the pixel we're checking, first of all, is white, then it's not an edge, it's just a background piece, and we get the coordinates, and then we push that into the white pixel vector. I print out the sizes just to see how many black pixels ratios we have to white pixels, because if there's more black pixels than white pixels, then my program wouldn't be working right. Then I say, okay, at those positions we found all the white pixels at those positions we found all the white pixels, like the non-edge, I want you to fill them in with the color white. At all the pixels that were found to be edges, keep them and fill them in as black just in case anything happens. Then I move that to get the chain code, and after the chain code happens, or after we get the numbers for the chain code, I print out the image. So we're going to go up to the chain code. There's the structure, the float x, float y. Alright, so the first thing we have to do is find the first pixel. We have to find the very first black pixel to start looking into our image, because we're assuming that the image is a complete shape with no gaps. So we haven't found the first pixel yet, just in case the user puts in a blank pixel. Excuse me, then none of this will run. Get the coordinates for that, or we create a coordinate variable to hold our x and y for that black pixel. Then we get rows and columns, so we iterate through the entire image. we look at the intensity of every single point in our new image, and then we try to see, okay, if we found that the intensity at the value that we're looking at is 0, then that is the black pixel we would start this this test from. So we print out the point, we get the pixels x and y, and then we say it's true, break out of this loop. If we found it, break out of the next loop so we can get out our yeah, I think it's embedded loop is what it's called. And then we go on to getting our chain code. So current pixel, yeah, we get some coordinates, and then we just say our current pixel equals our first black pixel we found's x, it's y. We have a string called false direction, which we'll see you'll use later. Random time, which I forgot to get rid of. Max iteration, just in case it gets stuck into a loop, and then the there. So while I is less than max iteration, it was set at a pretty high number just in case like it goes overboard. And you can get rid of this whenever and just put true. But I found with some images it could go into a loop, so I made this a max iteration so it stops. So if at char point, if at the point we're looking at, right, so back to this image. Okay, so if we're looking at this pixel, right, this is saying if the pixel we're looking at below is 0 and the false direction is north, then move the pixel south, but that's a condition for later. So let's actually start at this one. So this is where the actual check will start. If we remember from earlier, I'm going to be using a absolute coordinate direction of the 4 basic cardinal rules. It'll be east will be 0, north will be 2, west will be 4, south will be 6, and you always want to check it in a counterclockwise way. What this means so at the very beginning of our picture, this is the current pixel that we're at, and it'll say, okay, I'm gonna first look east of this pixel. Is that pixel a black pixel? Is my current direction, is my false direction east? Which I'll explain later why we have that. So, very first statement, it says, alright, let's look east based on these cardinal directions. Did we find a pixel with an intensity of 0? We found a pixel with intensity 0. And the false direction is not equal to east because right now it's empty. So it says, okay, take the current pixel's x and add +1 to it and make the false direction west. And what this is saying is we take our current points that we're looking at. We say, okay, now this is our current pixel, right? And we say that the false direction is west because if we don't say that, then the next time this pixel looks for its friend, say if we reach a corner like this, and we say, okay, we found east, and we're like, okay, it didn't find east, west, and then it goes back here, back to this pixel, and then it looks again east, and then from here it looks west, east, west, and you get stuck in a loop between these two pixels once you reach a corner. So we say the false direction is west, so it won't look back there, therefore it doesn't go backwards in how it tries to find pixels within the tree. So it's pretty much the same idea for the rest of them. If the pixel above is black, then we go up, or if the pixel above is black and our false direction isn't equal to north, then we move the current pixel north, false direction south, C out 2, which is this again, C out the C out that absolute coordinate. West, if the pixel west to us has a scale of, or an intensity of 0 and the false direction isn't west, shift our current pixel to west, false direction is east, print out a 4. And then lastly, south, if the pixel below has an intensity of 0 and the false direction isn't south, then the false direction's north, and we move our pixel down 1 and see out 6. And then at the very end, if our current pixel equals our original coordinates, then we're done looking. And then we iterate 1 up. Now, the reason I have this up here, and this is basically south, a check for south, again, is if when you decompose, or when you make the outline of the picture, you have a structure like pixels like that, you can run into some problems. So let's assume we're at a corner, right? We decomposed our square, but on one of the corners we have a structure like this. So these are white. Right. So when we found the image, we found that these are white. Everything on the outside's white. But this pixel right here was found to be an edge. And that's something you need to add in more cases for to fix. But in case you can't, what happens with this error is it'll start from this pixel and go to there. And then this pixel will look and say, okay, my false direction is east, so I can't check that pixel. This one's white, this one's black, so I'm going to move here. It moves here. My false direction's east, so I ignore this pixel. That's false, that's false. Oh, I can go south now. Now, if you didn't have that condition I have it above, what it would say then is, every time we look at a pixel, it always checks east, north, west, south, east, north, west, south. It always starts at east. But if you do that, then it says, oh, this is a pixel. Right, I'm going to go here, and now my false direction is west. It's like, okay, I got white here, and then it was like, okay, I have north. It goes there. Now my false direction is south. Now I go east. Now my false direction is west. And then you get stuck in this endless loop right here. So what you do instead to bypass that problem is, since south is always going to be the last one it checked, what this is saying up here is that if south was the last thing checked, we're going to start checking at south first before east, which in picture terms is we start checking here. Oops, change that to a square. We start checking at this one and then move counterclockwise. And because we do that, it'll say, oh, hey, look, here's a black pixel. And it'll start going down as intended and ignore this pixel. So that's how the code works. And then at the end, it doesn't return anything. It just prints out. I'm gonna first start this with a test image. So it decomposed the image, and this is what it came out with. And OpenCV has this weird thing with, or at least not OpenCV. Sorry, my code, the outline code I made is doing this thing where it makes it bigger. But basically, what it's saying is, okay, we're starting at this pixel all the way down here, right? We're going to move east 580 times. So then it's back here. Let me see if I can draw a bit bigger. So it's saying, I'm going to move east 500 times. And then we see that shifts 2 right here. 2, 2, 2, 2, 2. 2 is north. So it's going to shift to 50 or 60 something times. See here at 4, then it goes east the same amount of times. Or sorry, west the same amount of times. And then we have the 6s here. Shift. Once our max, and then it keeps going in a loop, and then it hits the max iteration, then we're done. So now let's test it on something that's Oops. The other image I have saved. Alright, so this is the image that we start off with. This is weird looking donut ring that has the bottoms chopped off. This is the outline that the program creates. What it says is it starts off down here at the bottom. Okay, we hit 0, and we go... make this... But we start from here and we go down, right? Go across, and see the 2s get sprinkled around. Go up, 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 up. And then eventually we hit a bunch of 2s. We can assume it's this point right here of the image. And then we go west 2, and then we slowly traverse back up. And then we go west and then down where the 6 is at. Now you see 6 is sprinkled around. And then as we go down, you see it starts getting the numbers start getting crazy, and that's this structure right there. And so what we can do with these numbers is say, hey, if we had an image that looks similar to this, then that is the Marina logo. Basically it. And then this is there's found 928 black pixels, 6,608 white pixels, and that's the coordinates that we started off. And that is chain code. Yeah. And then it's free to press a key so it doesn't terminate. Turns, and thanks for watching.